Okay, this is my lab 2. So my introduction, the purpose of the experiment was to investigate the distance dependence of a magnetic field produced by a permanent bar magnet. Using a smartphone magnet meter, I used Tesla meter, a meter stick. Measurements of the magnetic field were taken at various distances from the magnet. These measurements were used to determine the relationship between the magnetic field strength and the distance expressed as the distance dependence equation right here, B equals KR to raised to the N. The experimental results were then compared to the theoretical prediction for an ideal magnetic dipole. In addition, a computational model was based on the dipole magnet was used to develop and predict the magnetic field of an off-axis location. Some of his concepts that were used was this equation right here, the magnetic dipole field equation, where mu naught is the permeability of free space, r is the distance from the magnet, mu hat is the magnetic moment, and r hat is the unit vector from the magnet to the observation point. Systems and surroundings, I said the system was the bar magnet, the magnetic field produced by the magnet, and the smartphone magnetometer, and then the surroundings were the Earth's magnetic field, and then the table in the room environment. So for the lab, this is the picture of the lab I used with there's a Tesla meter and the meter stick. And then for the lab, for the what we actually did in the lab was first smartphone app was used to measure the magnetic field components. The phone was aligned to the north, so the X component of the Earth's magnetic field was approximately 0. A meter stick was then aligned east to west, and then the magnetometer sensor location where the phone was identified. Next, a bar magnet was placed along the meter stick and the distance between the magnet and the sensor was adjusted until the magnetic field strength was these 5 right here, which were measured in the X direction. 3 measurements were taken at each field strength and recorded on the spreadsheet. The data was then analyzed and plotted at ln bx versus an ln r to determine the distance dependence of the magnetic field and calculate the exponent n. The intercepted graph was then used to determine the magnetic moment of the magnet. And then finally, an off-axis measurement was performed by placing the sensor at a 45-degree position relative to the magnet. The magnetic field components were measured and corrected for Earth's magnetic field. These results were compared to predictions of the computational model. So here's the data. Here's my spreadsheet where all the data I collected through the Tesla meter that I was able to get. And then I was also able to determine that when the magnetometer was far away from the magnet, it measures a near zero magnetic field in the X direction. And as the magnetometer moves closer to the magnet, the measured X component of the magnetic field increases. So distance dependence, the distance dependence describes how the magnetic field changes as the distance from the magnet increases. During the experiment, the magnetic field strength was measured at several different distances from the bar magnet. And as expected, the magnetic field became weaker as the sensor moved farther away from the magnet. Using this distance dependence formula right here, and then by plotting ln b versus ln r, the slope of the graph gave us the exponent of n. So then I built a computational model. This was used for the magnetic dipole field equation to calculate the magnetic field and produced by the bar magnet. After finding the magnetic moment, the model predicted the magnetic field at 45-degree observation point, and these predictions were compared to the measured values that were I found in the lab. So the results to test the dipole moment, I measured the field at a 45-degree angle, like I said, and compared the values to the model I just made. The experimental magnitude was approximately 6.8 times 10 to the negative 5t, while the model predicted by the code was 2.85 times 10 to the negative 5. And then, although these were different, the model one was correct or predicted the overall what the behavior should be. But I said the distance is likely due to the uncertainty and the fact that the real bar magnet is not a perfect magnetic dipole. So the first what-if question, I answered if the setup had not been aligned with the magnetic north, Earth's magnetic field would not have affected the X component measurements. This would make it harder to isolate the magnetic field of the bar magnet and would introduce additional error into the calculated distance dependence of the magnetic moment. And the second what-if question was if two identical magnets were stuck together end to end, I would expect the field to be stronger. Since the magnetic moment would approximately double, I said that the new mu would be two of the old mu, and then since B is with U, so the measured magnetic field would at the same distance would be about twice as large, since the magnetic moment the magnetic field depends on the magnetic moment. So in conclusion, this experiment investigated how the magnetic field of the bar magnet changes with distance. The results showed that the magnetic field decreases as the distance from the magnet increases. Consistent with the behavior of the magnetic dipole, a computational model that I built used the magnetic dipole field equation and predicted the magnetic field at 45-degree location and was compared with the experimental method. Overall, this experiment demonstrated how magnetic fields can be measured, modeled, and analyzed using both experimental data and computational models. That's it. Thanks.